Good morning, everybody, and welcome to How Do You Design a Spacecraft with Emma Forbes Laird. So, thank you very much for joining us today, Emma, and we really look forward to hearing about what you're doing in the space industry.
Good morning, everybody. I'm here from Airbus today. That's my day job. I work for Airbus Defence and Space in Stevenage, and I work on digital processors on space satellites. So I thought you might like to think this morning a bit about what we have to do to design a spacecraft, because as well as the bits that I work on, as you might imagine, there are big teams of people who have to work out how they get these spacecrafts into space and get them working. So, in order to design your spacecraft, what do you need? Well, the first thing to think about, I'm just changing my slides here, hopefully, is think about what do we use these satellites for? So we've got to design something, we've got to make something that works. And actually, you might not realise how much satellites are used in everyday life. So, for example, you or your parents might have a mobile phone. It might use standard signals, but if you think about satellite phones and mobile pagers and GPS in the car, anything like that that has a signal that shows you where you are on the earth and tells you where Google Maps is as you're wandering around lost around a city you don't know, all of those things use some form of satellite. And also, if you think about your TV, those of you who are watching the football, I think we can watch it on BBC or ITV or something. But sometimes sport and other channels are on Sky TV. And again, people have a Sky dish, and that's taking in a satellite signal. Some other ones you might not really have thought about so much is actually business transfer. Anyone who understands, things like the stock exchange, where money is moved around very quickly, they have to move information, data all around the world between New York, Hong Kong, London, Europe, all over the place. And that has to happen quickly. And quite often that might be using satellites. So some other uses of satellites that maybe aren't so obvious, maybe you don't see so much, is they're used in observing the world. So search and rescue operations, we've had a few people in the news recently, sadly, lost in different areas of the world, you might have seen. And one of the resources that these rescue teams have is that they can call on satellite images to try and figure out where people are. When there's forest fires that take place, which we've had many of in recent years, again, they can use real-time data from satellites to monitor how that fire is spreading. And if you think about the sort of climate concerns that we've had for the last, decades really, about melting ice caps and things like that, how do you think we know that? A lot of that data comes from satellites that are going around the Earth, taking pictures or measuring a particular water level or measuring temperature or something like that from space. So actually, you'd be surprised how many spacecrafts might be involved in your day-to-day lives that you didn't realise. So the basics of a satellite or a spacecraft, really. So when it is up there, it has to do its job, whether that's taking photos or downloading data, or as a communication satellite or sending TV signals. But it has to also have a signal that connects it to the ground, because it needs to send its information to the ground, or it needs to receive information from the ground. Obviously, you need to be able to control your spacecraft, because you can't just put it into space and let it drift wherever. So we then also have ground stations. So we have an uplink signal, which is signals going to the satellite, and we have a downlink signal. So you started to think about what these satellites do, what these spacecraft do, and where are they? That's the other interesting thing about designing for space. Our spacecraft are generally a long way from the Earth. You often don't have just one satellite as well. You might have a whole set of them. So, for example, one satellite might be taking pictures of a certain orbit around the Earth. It might be taking photos of polar ice caps. But then you might have another camera that is able to look more around the deserts, around the centre of the equator. And if you have communication satellites, you might want to be able to send a signal from any one place on Earth to any other place on Earth. And if you want to do that, You might need several satellites in combination to be able to pass that signal along. And satellites are also in different orbits. We have things called low Earth orbit satellites, which are often passing quite close to Earth. Some of you might have seen Starlink satellites. They're our competitor, obviously not Airbus, but they have launched big constellations, lots and lots of satellites, and sometimes you can actually see them being launched as tiny little blobs of light if you happen to catch them in an evening. Some of you may have seen the International Space Station going over, because that is visible to the naked eye. Again, those are all in very low Earth orbit. Although they look a long way away, compared to other spacecraft, they're actually quite close, because some of these spacecraft might be out at 30 or 40,000 kilometers away from the Earth, which is a very, very long way. So when we think about designing for space, we want to make this spacecraft. We want something maybe that is going to help with a GPS signal, or it's going to monitor forest fires, or whatever we're trying to design for. What do we have to think about? Obviously, in engineering, we do a lot of work on our cars, our mobile phones. We want to have, the latest games. We want it to have the best battery life in our phone. We want something that doesn't stop working suddenly and be a pain and have to be fixed. So obviously, you want similar things for your spacecraft. You want it to work well, but because it's in space, you've got some very special challenges, really, that you've got to think about right from the beginning of your design. The first one is space is a very different environment to being on Earth. There's no air, there's no atmosphere. It's a harsh environment for radiation. You get lots of radiation from the sun, you get solar flares. Those of you who saw the aurora will know, even though the sun is such a long way away, we can see the impact of solar activity. The other thing about space is when you're in the view of the sun, your spacecraft might be heated up an awful lot, but if it's in shadow, say it's behind the Earth relative to the sun, then it would be much, much colder. So there's a huge range of temperatures that change. So the trouble is that's very different to on Earth, where, in the daytime in the summer, if we're really lucky, it might hit about 30 degrees, and overnight, even in the depths of winter, it might get to -10 or something like that. Those are the extremes of temperature, but in space, the temperature range can be much bigger. So what we have to do a lot of work thinking about all our components, our chips, as to how we can test them on Earth to show that they'll last and that they'll be able to cope with a space environment. The other thing we need to think about is building in redundancy and robustness. And what that means is, again, if you think about your mobile phone, I happen to have an Apple phone. If it goes wrong, I go to the Apple store and I say, right, there's something wrong with my phone. Look at it, please. And they might take it apart, or they might run some diagnostic tests with software. And they might say, oh, that part needs replacing, or I'm terribly sorry, Emma, this phone isn't going to work anymore. We'll have to give you a new one. Or they might simply say, oh, look, we fixed it with software. But when you've got a spacecraft that might be 30,000 kilometers away from the Earth, once it's there, you can't take it to a shop. You can't pop up there and just replace a part. You can't go, oh, whoops, bother, never mind. Let's put another one of those chips on. This one will be fine. So you have to think very carefully about your design, and very importantly, your testing of your spacecraft and all the different bits of your spacecraft to make sure that it's actually going to survive in space. The other thing you might not have thought about when you're designing something for space is it's also, as well as having to survive in that space environment, it's also actually got to get there. I know that sounds a bit silly, but again, if my phone might be designed in a factory, and it might be, in a different country. It might have been made in a different part of the world, and it's packaged up in its box, and it might go, on a boat or a plane or whatever, and come to my shop, and I go in and I buy my mobile phone. Okay, that's not that hard to do in technology terms. But remember, this spacecraft has got to be delivered up to thousands of kilometers potentially above the Earth. Or if it's a space telescope that's looking out into the universe, it might have to be go an awfully long way away from the Earth. And how does it get there? It gets there in a launch vehicle, which is our posh word really for a rocket. So all of these spacecraft have to be, although we know how we want them to be when they are up in space, we know what parts, what size we want it to be, we've also then got to squish it down in size and in weight so that it will fit in a rocket. And actually, that launch vehicle, that rocket, if you've seen any of the footage of rocket launches, there's an awful lot of noise, there's an awful lot of shaking, there's an awful lot of temperature, heat, and actually trying to get your spacecraft to survive just that launch vehicle journey, to fit in the rocket and survive that journey, takes an awful lot of engineering before it's even got to where it's going to do its job. So start thinking about what you think your design might have to do. So you want this spacecraft, you want it to take pictures or process a signal or something like that. So what do you need to think about? Well, you want something that's going to survive out in space and survive that launch that we said was pretty tough. So you're going to have to get some sort of structure that's light and strong. The next thing to think about with your spacecraft is, how are you going to power it? You think about your mobile phone, you plug it in, it has a battery, but you have to plug it in, you have to charge it. You can't just plug in a spacecraft in a week's time, so you have to think carefully about how you're going to power it. So what sources of power have you got in space? Well, basically, our main source of power is either something that we have put on the Earth, so say a battery, or propellant that would make an engine that you could get power from, or it's from the sun. And that's critical to most spacecraft, is gathering power from the sun. And the other thing is, how will it stay in its correct orbit? So, you want it to go and take pictures of a certain part of the Earth. You've got to be really careful about exactly where that spacecraft is, where its cameras are pointing. It's no good if it's flipped round and facing the wrong way. So again, you've got to think about what you need on your spacecraft, and we call that an attitude and control system. So you have to make sure that not only can you position your satellite exactly where you want it, whether it's near the Earth, out into space, you have to know where it is, you have to be able to put it in the right place, and you have to be able to point it in the right direction. So that might be to take the pictures or to send the signal. But also remember that you've still got the issue that you've got to get power for your satellite. So you've still got to point towards the sun in some way to collect energy from the sun. So there's an awful lot of bits of your spacecraft that you've got to point really carefully. So those are the main things you think about in your design. So I'll show you now the sort of design of a lot of spacecraft and the sorts of important items we need to address those issues. So your main bus, we call it a bus. I know it doesn't look like a double-decker bus, but the main structure of the satellite, we call that the bus. And that has to be light, but very strong, able to cope with launch and able to survive for quite a few years in space without falling apart. We then have what you can see, the large, if you like, look a bit like wings sticking out. Now, these are critical to most spacecraft, and those are the solar arrays. So those are basically solar panels, like people might have on the roofs of their houses, and those are capturing the energy from the sun to continue to power the satellite. And then you might have almost certainly some batteries on board, because you might be pointing at the sun nice and strongly now, but if you went round the other side of the Earth and you're in shadow, you need to store some energy so that you can still use your systems of your spacecraft even when you're out of the sun. So you might have some batteries on board. You'd have some sort of a control system. You'd want something that is making sure that power from the batteries gets to the orbit control system to make sure that everything's working on board. You'd need some sort of antenna system. Even if your satellite is up there, whatever its job is to do, as we saw from the earlier slides, you've got to be able to communicate with the ground. Even if it's not a communications satellite, you've still got to be able to tell it what to do, and to know where it is. And if it's sending pictures down, obviously the satellite will need antennas to be able to deliver its pictures back down to Earth. Altitude and orbit control system, well, that's really what we've talked about. So that's a whole system that keeps it at the right altitude above the Earth, or the right distance away, and also over the right part of the Earth, so travelling around the Earth in the right orbit to make sure it's where it should be. And then, as we've said, you've then got to keep bits of the satellite pointing in all the right directions. And your last thing is something called a payload. So we don't put these spacecraft up just for fun. I'm sure that some people might think we should do it just for fun, but usually the spacecraft is up there to do a job, as we've gone through, whether it's taking pictures, whether it's processing a signal, providing information. All of those things are what we call the payload of the satellite. If you like, the payload of the spacecraft is the reason that we've put it up there, because this costs an awful lot of money. If you imagine, you have to launch it, you have to design it, you have teams of people, clean rooms, equipment, and so your payload is the reason that you're putting that satellite up there. It's the job that it needs to do. So hopefully I've given you an idea today of the sorts of engineering you have to think about for space. And there are an awful lot of people in Airbus, in Stevenage, and in plenty of other companies who spend their lives working on particular parts of the satellite. So in my case, I work on digital processors. So that is the payload, as we've just talked about. That's the actual operation of the satellite, what it's up there to do, and I design the processors for communications satellites, so processing lots of signals for a customer up and down, and doing that in a very efficient way to make sure that the satellite operators can provide those communication signals to planes, boats, parts of the world where there isn't a standard mobile phone signal. So that's what I work on, the payload of the satellite. But there are all sorts of interesting jobs looking at all aspects of spacecraft and how you design them. So thank you for listening today.